Copy that down. Write that problem down. Now, honestly, we looked at it in the last video. You could solve this without even knowing anything because you already know the unit circle. You already know all the information. But we'll take a peek at it. So again, the prompt is solve this equation. To do that, what does that mean? Yeah, right. Same as always. We're finding the solutions, we're finding the roots. So we're going to take this thing and set it equal to 0. Done. Yeah, I got to add 1 to both sides, divide by 2. You do the work. Right, yeah. So look, it's pi over 6 and 5 pi over 6. Uh, okay, did I solve it though? No, I didn't. You watched the video, the last one, when we looked at the graphs on Desmos. How many solutions are there? Right, like infinitely many. Now, the graph doesn't actually look like that, all right? So get over it. It doesn't look quite like that. Whatever. It has infinitely many solutions. I need to represent that. So I have pi over 6 is one of them. Now, if I cross the x-axis at some point, which I do, right, that's my solution. I cross it at pi over 6. When's the next time that I'm going to cross it? Well, we could answer that question looking at a graph, or we could answer it looking here. Okay, so I'm at pi over 6. If I add 2 pi, I'm back in the same place. If I add 2 pi again, I'm back in the same place. What does 2 pi represent? Yeah, the circumference of the circle, but it also represents the what of the function. There's no b here. The b is 1, which means you go 2 pi over 1. That gives me a period of 2 pi, right? That represents a period. So, in other words, look, this guy has a solution at pi over 6 plus 2 pi. Is that it? No. I want to represent every time this crosses the x-axis, which happens every 2 pi. Happens every 2 pi. So it happens at pi over 6 plus 2 pi, pi over 6 plus 4 pi, plus 6 pi. So 1 pi, 2 pi, 3. I can represent that with what kind of a number? No, not a real number, not a complex number. Kind of a whole number, an integer. So I say 2 pi k. And I also have another solution. It's just the same, 5 pi over 6 plus 2 pi k, because those solutions happen every 2 pi. What do I mean by that? I keep saying that. I mean literally, like, if I add 2 pi, I'm in the same spot, right? Like when we're doing rotations and we add 2 pi, right, we're in the same spot. Add 4 pi, I'm in the same spot. 6 pi, I'm in the same spot. That equivocates, like this circle, remember, becomes a graph. It gets unraveled. So every time this or this is happening, I have a root, I have a solution, I have an x-intercept. So plus 2 pi k, where k is any integer, and if you don't write that down, your problem is wrong. So here's my solution set, where k is any integer. There it is. Now absorb that completely. This is our second problem. It's find the roots or solutions or solve cosine squared x minus 1. So solve it. Are you stuck? All right, look. Use difference of squares, all right? Cosine squared x minus 1, that would be something, something, right? Something plus, something minus. 1 and, yeah, cosine. That's the definition of difference of squares. I've got a squared minus another square. I use that. That's how I factor. In other words, key here, I've got to factor the stuff. From here, you set each of these factor groups equal to 0, right, and solve for them. So find all of the roots, and don't forget, we've got to talk about the period too. Go solve it all the way out. Right, I've got cosine is equal to -1, that happens at pi. Cosine is positive, that happens at 0 or 2 pi. Right, those are the radians, those are the solutions. Now I've got to talk about it across the entire coordinate plane. Okay, you should be here, you should do this on your own. I have pi plus what? Why? Yeah, because I go around the circle infinitely number of times. I talk about that as 2 pi k. And what about here? I can just say 0 plus 2 pi k. Well, I don't need a 0. That doesn't mean anything, so I can just say 2 pi k, right? So this happens at pi plus 2 pi k and 2 pi k, where k is any integer. Done.